Matthias is a senior solutions engineer at Citrine Informatics, working directly with customers in Europe to help them get started with AI effectively. He was previously a lab team leader at BASF, where he led high throughput screening projects for paints and coatings. Let's give a big welcome to Matthias Herman.
Thanks, Scott. So very excited to be here today and tell you a little bit more about data-driven approaches for material development. And as you can see by the title, this is something that I'm going to show on the example of polyurethane foams with a specific focus on how we can cut costs and maintain flammability compliance with such a data-driven approach. So when developing materials, may it be a polymer, may it be also another material, there is a lot of challenges that we are usually facing and that require a lot of experimentation. Those challenges and goals that we are trying here to achieve are, for example, the final properties that we would like to achieve. In the particular case of polyurethane foams, it might be finding a good thermal conductivity or a low thermal conductivity, high flame resistance, density. It might be then also something like the mechanical stability and minimizing the cost at the same time. So those performance objectives are often competing to each other. And so the goal is to find a sweet spot there. Not only are we trying to optimize for those properties, at the same time, we have some other conditions, external ones that we need to fulfill. Those might be regulatory requirements. A lot of you might be available about PFAS, which is something that is not allowed anymore, PFAS-containing additives in polymers that need to be limited while still achieving those performance objectives at the end. Phthalates might be another example, and there is more and more regulations coming up, and so it is required to be able to quickly adjust to those requirements while still achieving target properties. Along those lines, we have also sustainability mandates, for example, achieving or adding a certain amount of recycled content in your material, and also having materials that are compostable at the end. And last but not least, supply chain volatility. The situation where we might have a raw material that's been delivered or that's been available to us for a long time, which might be at one point not available anymore, or that undergoes a high change in the price, where we need to quickly adapt to it. Finding an alternative while still achieving the performance objectives that we are setting up is also a challenge. Now, how are we dealing with those challenges? How are materials developed? May it be polymers in general or polyurethane foams? It requires experiments. A lot of experiments are possible when we consider all the different ingredients that are available, when we are considering different process parameters that are available, and it becomes clear quite quickly that you cannot test everything. There's just way too many combinations in order to find the perfect solution. And so what needs to be done is we need to rely on experts' experiences, the intuition that they're building up over years in order to find a good solution. However, when going that way, there's also the risk that we are narrowing the space too much. Experts might have also biases, are drawn towards different solutions that's been working in the past, but when we're replacing some ingredients or finding new solutions, those biases might be also a little bit counterintuitive or might be also counterproductive. And what can happen is that weak candidates are surviving too long in that entire process. They might survive some first initial tests and then are tested further, and then might be qualified for some expensive certified tests and then fail at the end. And this is a situation that is usually something that we would like to avoid. Getting strong candidates early and making sure that they are proven to work at the end. Now, an AI-driven approach can help you to get quicker to those strong candidates and eliminate weak candidates early on, especially in a multidimensional problem, as I described it here, where you have a lot of different competing objectives. such as the cost, such as the performance, and all doing that at the same time as quickly as possible. And this is something that is not only something in theory, it is actually happening right now. That is used currently by some of our customers. Here's an example from Huntsman Building Solutions that are using the Citrine Platform in order to optimize polyurethane foams and find quicker solutions that are fulfilling their requirements. So they approached us and started working with us, and were aiming to the following objectives: accelerate the development and building a framework that allows them to quickly respond to customer requirements and develop materials that are fulfilling those requirements. One of those requirements being a flame retardancy test, ASTM E84. And with that model that is then going to be built, the goal is to reduce the amount of large-scale fire tests. Those tests are very, very expensive and take a lot of effort to set up. So you early on want to eliminate any weak candidates and not test too many in that large-scale fire test. At the same time, the goal is also to understand some correlations that are hidden in the data. Not only to get a result, like a black box result from an AI model, also understanding how the model is thinking. What are the inputs that are utilized? Which ones have a high impact on the flame retardancy? This is also one of the objectives that was aimed to be achieved. And so what was done is basically an AI model was built with the platform. This is something that I'm going to show you also later during the webinar live, how we can build a model with just a few clicks. And there, a model was built that predicts the structural stability, the insulation, and also the flame retardancy. And what happened is then that the researchers were testing some suggestions that were provided. The tests that they were doing were actually only small-scale tests at the beginning. And we were then able to build a model that correlates the result of that small-scale test to the likelihood of it passing the large-scale certified ASTM normed test. And then we were able to get that correlation and early on detect candidates that have a high likelihood of succeeding here. And with that, the overall process was accelerated. Using data that they have already collected, that we're able to collect also quite quickly in the process, that was fed into the system. And then within a few minutes, the platform was giving you suggestions that have a high likelihood of achieving all those different competing requirements, while also fulfilling certain regulatory requirements that were defined beforehand. Not only that, the last objective was also to better understand how the model is thinking and what the correlations are within that material. And this is something that the platform is also providing. It is not a black box. It is something, it is able to show you what the correlations are like, what kind of inputs have a strong impact on the final outputs. And it also tells you how accurate the model is and what confidence it is in predicting certain properties at the end. And what I want to take home from that is also that the platform is something that you can use directly as a scientist, and you do not need to be an AI expert. You do not know how to program or code. It is designed to be used by experts themselves that are developing the materials in the lab. And you also need not a lot of data. You can get started with the data that you have currently, maybe 20, 30 data points that are relevant to the material that you are developing. This is a good starting point that you can get onto the platform in order to build a model with a few clicks and then directly get suggestions. The nice thing about that direct approach, about it being used as a tool for the researchers themselves, is they can directly implement the knowledge that they have. Because it's not just about the data that is giving a good prediction. It is also important to know the kind of details, the rules that need to be fulfilled, that often are in the minds of those experienced scientists. And by having that direct connection, not a person in between that translates a problem first into a model and then also translates those results back for review by the scientist themselves is using directly that platform in order to accelerate process, the development of material. So how does that work? Let's get into the details and let me show you what the workflow is in order to achieve that. It all starts with the data. As I mentioned earlier, we need some data in order to get started and build a model. That data is usually data that was collected already in the past, that the research groups have already on similar materials, on materials that they are already selling, and this builds the basis for the model. We can get started with only about 20 data points in order to build a model, and that model does not require any coding. You can generate a model with just a few clicks, and you can adjust the model, entering your experience, expertise, making sure that certain correlations and rules that you are following when developing a material are also represented in the model. And then that model is able to make predictions for the properties that you would like to optimize. However, when you are getting those predictions, we have a huge space. We have a huge different amounts of combinations that might lead to a solution. But only some of them make physically or chemically sense and are reasonable. So we need to set constraints on the formulations that are allowed, and this is done in that third step, the search space. Here we are defining how much of a catalyst should be added to a formulation, how much of a flame retardant should be added. Setting boundaries, making sure that the results or the area within which the model is looking for a solution is reasonable. And then you are setting target properties. All those target properties that I might have mentioned at the beginning. Mechanical stability, flame resistance, at the same time minimizing the cost, and so on. So you just make a wish list of all the properties you would like your new formulation to have, and then the platform performs a multi-objective optimization. It's looking to optimize for all of those properties at the same time, and what you are getting is a list of potential experiments that have a high likelihood of achieving those goals. The platform not only gives you those formulations that have a high likelihood of achieving those goals that you want, it also gives you a prediction for those properties and the uncertainty of those predictions. So there might be some that might be not as accurate in the prediction because the model requires more data, but it's going to be transparent with you. You will then see, okay, my mechanical stability is likely to be in the range that I want, but my flame retardancy, it's not sure yet if it's really going to be fulfilled or not. So what we need to do is we're going to pick some candidates to be actually tested and then improve the model. When picking the candidates, you can then decide if you go for what we call safe bets. Those are basically formulations that are very similar to the formulations that you would have chosen by yourself anyways. Maybe something that is very common, where you just try to find a sweet spot between the different amounts of the ingredients, or you can go what we call exploratory experiments. Those are experiments which are more considered outside the box, more crazy, more different than what you have done in the past, but where the platform says those might also work, and those might be also very worth testing, and you might get some new ideas. This is a good way to remove biases, especially when you've been working on a material for a long time and you are always following the same rules. There might be patterns in the data that reveal that other combinations might work as well. And then you can decide if you go rather for those safe bets, those are really similar to what you've done in the past, or try some other formulations that might be quite different. You take then those into the lab, test those, and you might then get directly a solution that works and fulfills all your requirements. If not, then you are feeding the results and the data back into the system. You're extending your data set, retrain the model. You have then a model that is improved, that is learning from the data that you collected. And then you get a new set of candidates that you can then also start testing. And it's up to you how many of those candidates you are testing in each round, what type of candidates you are testing. And then with every cycle, you are improving the model and getting closer to those desired final properties. So this is how the workflow looks like. And now I would like to switch to the platform and show you live how the platform actually looks like and how it is for a use case, such as for optimizing polyurethane foams. So let me switch to the Citrine platform. And what you can see here now is basically a project. This is the landing page for a project on the Citrine platform, which is running live now. And the first thing that you can see here is that described workflow, that 4-step process where we start with a training set with the data that you currently have in the lab, then building a model based on that here in that second step with just a few clicks, then defining a search space where you are setting the rules on how much of each ingredient should be used, what type of ingredients are allowed or not in your formulation. And then you get at the end what we call candidates. Those are those formulations that have a high likelihood of achieving those desired goals. So let me walk you through that process and see how each of the steps looks like. Starting with the training set. This is basically any data that you might have collected on polyurethane foams in the past. And here you can see we only have 39 data points, but this is enough in order to build a first model and get a guidance, get some suggestions on what the next best experiment is to do in order to achieve your target properties. And what you can do here is you can utilize it as a data management tool and also explore the data that you have. So some properties that you might be interested in is, for example, you would like to see in the past what kind of tensile strength your materials had and were you able to get those with a low post-curing time. Maybe that's a challenge that you have. You would like to accelerate the process of production, reduce the curing time while still achieving a high mechanical strength. So you can plot your results here, and then you can see, okay, we would like to have a short post-curing time while still having a high tensile strength. We can first of all see that there is a slight correlation between the cure time and the tensile strength, and that those are competing to each other. But this candidate here, experiment 22, looks interesting. So I'd be curious to see what we've done there actually. What were the process parameters? What were the ingredients? And this is basically then one of those 39 data points that we are using to build the model. In each of those data points, we have basically one material with the formulation information and the information that we have measured about that material. And it's all represented in that graphical way. And this is what we call the material history, because it contains all the relevant information of that material. On the right side here, we have the final polyurethane foam and all the measured properties captured. You can see here, we have the tensile strength that was also plotted, but then also the flame retardancy as an LOI value, then the open cell ratio, and whatever you are measuring. You have full flexibility on what properties you are capturing here, and those are usually the properties that you would like to optimize. Then what belongs also to that material is the process itself. We can see here, we have here information about the curing process, such as the temperature, the time, and also the mixing speed in order to get to that material. And then, of course, we have the formulation itself. You can see here what the ingredients are, how much of those ingredients are used, and also further properties about those ingredients. Those might be information that is available in technical data sheets or from your quality control when you're receiving batches and doing some general tests. You can get that information in here as well. And the platform will build a model where it tries to correlate all the relevant information. May it be the formulation itself, may it be the properties of the ingredients, the process parameters, tie those to the final properties that you would like to predict at the end. So the very first step is really to get all the relevant information together in the right context, making sure that we have everything organized here. And as I said, we can get started with as little as 20 of those data points in order to get a first model and a first prediction. Once we have that data uploaded onto the platform, you explored it a little bit, we can get to the fun part of actually building a model. And let me show you what it takes to build such an AI model based on the data. It takes one click here. You see we have already two models here. I'm creating a new branch with another model. A second and a third click, and the platform is now looking at the data that was provided and giving you a suggestion for a machine learning model and the data that is utilized in there. And that model is represented here in that tree. Again, no need to write a single line of code to install anything. You're just going to upload the data, generate a model, and then you will have that suggested model at the beginning. You can make adjustments here, but let me quickly explain what the model is actually containing. We start at the top with the training data that we just looked at. And from that training data, the platform is then extracting information that are used as inputs for the machine learning models that are here defined at the bottom. Those machine learning models are aiming to predict those final properties that we looked at, such as the tensile strength, elongation at break, performance during the flame retardancy tests, and so on. And information that is extracted as inputs are all related to the data that we provided. For example, I showed you for some of the ingredients, we might have a molecular structure also given or known. So the platform will then utilize those structures and then extract further information from those, such as the number of acid groups, the number of atoms, the molecular weight, and so on, and then generates even more features, even more inputs that it will try to correlate to the final properties. You can make adjustments to the model by adding nodes in that graphical interface. For example, custom formulas where you are also saying to the model, I also would like that the ratio between certain ingredients to each other is considered, or the ratio of one ingredient to a process parameter. You can define that as a custom formula here, tie it into the model, all with that graphical interface, no coding required, and very intuitive to be used. And then once you build that model, you just go ahead, click on train and validate, start training, and within 15 minutes and 8 clicks, you have basically your first AI model generated without being an AI expert. Once that model is trained, you are able to review that model and get an idea on how the model is thinking, what are the correlations it's finding, and this is all done here. It's not a black box. It is something that we designed to be transparent. So you also get insights and you also understand what correlations are found in the data. What we can see here are basically the models that were generated for those output properties, such as the flame retardancy or the LOI value, which is a measure for the flame retardancy of the material. And what we can first of all see is how well the model is performing. Those graphs here on the left side are basically showing how well the actual values are in alignment with the predicted values by the model. So the closer the data points are to the green line, the better the prediction is. And what we can see here, for example, is that the model is generally doing a good job of predicting that LOI value. However, for lower values, it tends to predict the value to be a little bit higher. And for higher values, it tends to be a little bit undershooting it. However, it is showing a good trend. It's a model that is good enough in order to get some first suggestions in the first round. Besides that, we can then also try to understand how the model is actually building the model. What are kind of the inputs it's utilizing? And this is something that we see here in the feature importances. We can see what kind of inputs out of all the inputs that we provided in the data that was given to the platform, which of those show a strong correlation to the LOI value here. And we can see the very first entry being the flame retardant, which is not surprising because this is exactly the job of the flame retardant. So it's a good way to confirm if the expected inputs, if the expected correlations are actually also found in the data, and how those correlations are actually looking like, or if there might be even some other correlations that you were not expecting. And then we can dive deeper and see how that correlation looks like by those feature impact graphs here at the bottom. These basically show us those experiments that we were providing as a basis for the model, those 39 different experiments. And we can see here on the x-axis the amount of flame retardant that was used in those experiments. We can see we have a few controls without the flame retardant, and then some with a little bit more. And then whether those have a positive or a negative impact on the value we are trying to predict. And so this helps us to see, is that a positive correlation, a negative correlation? Do we maybe have a saturating behavior at one point where it doesn't make a difference to add more flame retardant? And those kinds of insights can be found by exploring the models in more detail. So it helps us to really get an idea if those correlations are there that we are expecting, or if there is some other patterns hidden in the data. Now, once the AI model is built and we reviewed it, we can now go ahead and get some suggestions that are utilizing that model. But before doing that, we can restrict the search space, making sure that we're only looking for reasonable solutions and not for some crazy combinations that do not make any sense. We can do that, for example, for different applications where we would like, for example, to minimize the cure time or only use certain ingredients. And how that looks like is, can be seen here. We have a list of the different types of ingredients, such as the blowing agent, the catalyst, and so on. And here, your developers can define in what ranges those should be used. So if we look, for example, at the flame retardant, by experience, I might know, okay, I need at least 10% of the flame retardant, and anything above 16% is financially not viable, or it is not going to work because it will have a negative impact on the mechanical strength, whatever it might be. You can set here boundaries and then decide if you want the model to allow to look within a larger search space, or narrow it down and force it to look for a solution in a narrow range. And then within those, you can then also define what type of ingredients should be allowed or not be allowed. Maybe TDCP as a flame retardant is not allowed anymore, even though you used it in the past. You can then say exclude it from the suggestions. Don't give me any suggestions that utilize that. Give me only ones that utilize the other ones within those given ranges. Maybe you also want to allow it to use a combination of flame retardants. Then you can say, use a combination of a maximum of 2 of those. So there is a bunch of different ways to adjust the search space, set up rules. And as I said, that helps to really restrict the search space, get only reasonable solutions. But another big advantage that we see from our customers is it forces also the user to think about the rules, to kind of understand why they have those rules, or see if there is any rules that they're following. This can help to onboard new people because we have then here really clearly defined those correlations and those amounts that are allowed and not. And because this kind of information is often just in the minds of the developers. They know just by intuition, by default, of course you're going to use less than 15% of the flame retardant. But it's not always something that is written down or recorded. And so it's a great way to also capture that knowledge of people that might retire in the next few years or are leaving the company. Once you defined that search space, define the ingredients that are allowed to use, you can then also define boundaries for the process parameters. Maybe you would like to reduce the curing time, and then you can set a boundary here to give you only suggestions with desired properties, but within a 2-hour curing time instead of 8 hours, which was mainly used before. Once that is set up, we can go back to our workflow. And what we have now is the AI model that can explore a wide range of candidates. We now set some rules, narrowed it down in the search space within which we can look for candidates. And then in the candidate section, we are telling the platform what target properties we would like to achieve. Here you can see basically the objectives and constraints, such as we would like to maximize the LOI value for flame retardancy. At the same time, I would like to minimize the cost of my raw materials and the final formulation. and then also some mechanical properties that I would like to optimize. So you can make a wish list, provide all the properties that you would like to achieve. And this is where the platform is really good at, to optimize for multiple properties at the same time and finding a good combination of all of these. What you are getting as an output is basically a list of candidates. You can see here we have 100 different candidates that are suggested. We can pick, for example, the first one here. And what we are getting is basically a new formulation that was never tested before and that has a high likelihood of achieving those target properties. It tells you what ingredients to use, what amount, then also the optimized process parameters within those ranges that we were defining in the search space. And then at the top, you can see the predicted values. Based on the model, it gives you a prediction on what the values are and are they falling within the range, the target range that you are setting up here. So you can see some of those are outside that dark gray range, others are within that. And you can then decide where you want to put the focus on. You have 100 different candidates, and then you can say, okay, actually the elongation at break is more important for me. So you can go back to the overview, plot here the elongation at break, and then pick a candidate where the elongation at break, which is something that we also want to optimize for, is higher or lower, and then pick a candidate in here. And then get to those candidates, pick a few that seem interesting and you would like to test. And this is what I described earlier. Based on those filters that we have here at the beginning, you can then also go ahead and say, I'm going to choose some that are quite similar to what I've been testing in the past, or I'm picking some candidates that might be quite different to what we've been using in the past, just to see if those are also working. You can apply filters. You can force it to show us only candidates that have a low amount of flame retardant. So a lot of flexibility on picking those. And then once you pick the candidate, you would take it, go into the lab, and measure the actual, the actual value. Once you did that, you can record it here for training. And then we have, for example, here a formulation that was predicted to have an LOA value of 27. Maybe it was underperforming a bit, it was only 24. We would then enter the actual measured values, record it for training, and then it becomes part of the training set again. And that entire process is repeated. With the new data point, the model is automatically retrained. You will get a model that performs then better with each data point that you are adding. And then you can generate a new set of candidates and then repeat that process. And overall, the goal is, with the data-driven approach, really to get you quicker to those desired properties by giving you a direction what to test, instead of performing a lot of tests where you possibly optimize first for the flame retardancy, then you need to optimize in another set of experiments for the mechanical stability. By making the changes there, it then has again also an impact on the flame retardancy, which needs to be readjusted. So instead of doing that slow approach, the goal is here really tell the platform what you would like to achieve, all the goals that you have, and get as quickly as possible to all those target properties. All right, so that's for the live part of the platform. Let me go back to my slides and let me tell you a little bit more about the best way to get started and best practices. All right, so data. I mentioned a few times, data is the key part here in order to build a model. And what we are doing is we are utilizing the data that you have collected already. This is the data that is most relevant, that you can trust, that is, that was measured by your own researchers. And this builds the basis. Now, data can mean a lot of different things. We can have a small amount of data. We can have structured data. We can have unstructured data. And this should give you an idea with what kind of data we've been usually dealing with. And you can see we have here structured versus unstructured data on the x-axis and the amount of data on the y-axis. And what we see is the biggest part from our customers are Excel data sets. Those are considered structured data because those are machine readable. And a typical amount is less than 100. So what we often see, 60, 70 experiments in order to get started is what is mostly the type of data that we have. There is some cases where we have some semi-structured data, some data that also is contained in PDF documents or lab reports in text format, which we can also deal with and also integrate onto the platform. Another common use case are large structured databases where we have thousands of data points, but I would say this is something, as you can see here also, it's not as common. We have that every now and then, but what I want to show you here, it is not required. You do not need to have perfectly structured data. You do not need to have thousands of data points. The most common use case is just tens of experiments, data points that we can get started with. As I have shown you in the demo, 39 data points was the model based on. And this is something that we can get started with in order to get a direction and get a idea on what the next best experiment is to be performed. And this allows us to get quickly to a win, because using AI is something that is quite new for a lot of researchers and a lot of companies. So it is important to convince the people with an early win. And the way we're doing it is we are helping you to pick a problem that you are currently working on and evaluate it with you whether it's suitable or not to be used with the platform. If it's not suitable because it takes too long to measure a data point, or you might not have the absolute minimum required of data points, then we're going to tell you to maybe look for a different project. We want to make sure that we have that early win. And the best way in order to get it is to pick a problem that you're currently working on. Anything that is already ongoing where we can use the platform in parallel to support you in that development. And then we checking the data that you already have. Do you have any data? How is the data structured? And as you can imagine, we have seen a lot of different data formats. We dealt with handwritten notes up to perfectly structured databases. We will find a way to get the data onto the platform and get the value out of that. And then we are defining the search space together. We are checking with you if there are any constraints that need to be fulfilled. May it be regulatory, may it be some basic rules that need to be fulfilled for your particular formulation problem. And in order to do that, we have a team with a scientific background. A lot of our people in the customer support have done their PhD in chemistry or in material sciences, or have done their masters. And so we speak the language that you are speaking and can support you in order to translate those problems into data that can be valuable for the development of new materials. And then this is the way to quickly get some results, some experiments that are working, and prove that the platform is something that is beneficial to you, that it's worth investing more time in it, because we know change management is also a challenge. People have been developing materials in a certain way and might be a little bit skeptical about such new tools. And therefore, it is very important to have those quick wins and convince people in order to find then other projects that we can apply to that and scale everything up. It is something that's already ongoing and that's working. Here you can see some of our customers that we are working on. Those are the ones that are willing to publicly share that they are using the Citrine platform. There are a lot more that do not want to make it public. And you can see there is a lot of projects ongoing every month. We have thousands of experiments being suggested ongoing. And it is something that is happening now. And we see what potential it has to accelerate the research process. So in order to stay agile, to be able to have quick solutions, tailored solutions for your customers, this is a really good way in order to accelerate the process. Getting starting to, if you start tomorrow, you can get a technical win within a few weeks and see that it's working with such a data-driven approach that is supporting you in the development. I've shown you the use case at the beginning on the flame retardancy testing of polyurethane foams. Feel free to scan the code and download that use case. There is a bunch of other use cases that we have on our website. And with that, I'm happy to answer any questions that you have. And yeah, thanks for your attention. All right.
So yeah, as a reminder, if you have any questions, please put them in the chat window. Matthias, there is one that it actually came in fairly early in the presentation. Is there a special format the data needs to be in?
Good question. So we have different ways of getting the data onto the platform. The most common one that we are utilizing is a standardized Excel template. It's a multi-tab Excel sheet that we are utilizing, where you define what are the ingredients, what are the recipes, what are the process parameters, and what are your final properties. And this is the format that we most commonly use in order to upload the data onto the platform. Because we have seen a lot of that data that we are dealing with is captured in Excel files. I showed you that graph earlier, that structured data, 60% in Excel files. And so, yeah, we have seen that this is one of the easiest way to get the data onto the platform. Another way is to also build data pipelines. So if you have a structured database with a lot of data, then we can also utilize an API to feed data into the Citrine platform. This might be interesting, for example, for data that is continuously changing, such as price data. If you have raw materials where you have weekly or daily changes in the price and you would like to have always the up-to-date price on the platform to minimize the cost of your formulation, then we can do also a straight integration through a database and feed the data directly into it through an API. So yeah, there are a bunch of different ways, and I would say the most common format or the special format that we are utilizing is a Excel template. Great.
I actually have one on my side. How much data do you need to get started?
I'm sorry, could you repeat that question?
Sure. How much data do you need to get started?
Yeah, exactly. Not a lot. So 20 is the minimum of data points that we have seen to work in order to get a model with a first guidance. And most commonly what we see is between 20 and 80. This is like a really good amount of data. It always depends also on how much information you have besides that, right? I showed you a data point. It could include also a lot of information about the raw materials, or it could be more simple. But basically, I would say 20 data points is the minimum of data that you need. We have also customers that do not have a lot of data or just getting started with the project and work with us there. Here we can also support you in getting the first data points by giving you a suggestion what the first set of experiments should be to get those initial 20 data points.
And then we had another one come in from one of our attendees. Can you comment on what algorithms the multi-objective optimization uses?
There is actually a bunch of different AI models that are checked in the background. If you want, you can pick specific ones if you are going more into the details, but usually our users, they just want the model that performs the best. And the platform is doing that automatically in the background. So there is a bunch of different models it can choose from. We use mostly a multitask random forest algorithm. This is something that has proven to work quite well. but there is a bunch of other ones that might be picked depending on the sparsity of the data, depending on how much additional data you have. And so, yeah, you have full control on what model to use, or you can allow the platform to just pick the most effective one.
I actually have another question from my end, and I've seen this. We've done a number of other presentations in AI. We've had multi-day events, and I see some iteration of this question pop up more often than not, and that's, how do you keep people's data safe?
Oh yeah, great question. We know that data that is used as a basis to build a model is very valuable. It's your research data, it's this data that you collected on materials, and we treat it with the uppermost care. So it is, we are ISO certified, ISO 27001, and make sure that the data is not leaving the instance. It starts already when we are preparing the data set and you are sharing the data with us. We have secure ways of sharing the data with each other. And when you are getting one of those instances of the platform, it is only accessible to you. You will have the admin rights, you will have full control who will have access to it or not. You can decide whether you want us to also have access to it in order to support you, or if you want to keep full control. You can define teams where you can assign different users to. So if you have, for example, different projects within your corporation you're working on, and you want only certain people to have access to certain data sets or projects, you can also assign that. And yeah, we are aware on the value of that data that is utilized here. And you have seen the logos on my previous slide. Those companies would not work with us if we wouldn't make sure that we are treating the data securely.
Great. And then we've had another question. He started off by saying thank you. he asked the last question from the attendees. He said, I'm also curious how many objectives you usually see with your clients.
Good question. It ranges quite a bit. Some of our clients only care about 2-3 objectives to be optimized, but I've been also working with customers where we had 15 or more objectives to be optimized. Some of them are very similar. It might be a viscosity after 1 day, a viscosity after a week, and then a viscosity after a month. Some of those are tightly correlated, but I would say an average around six different objectives, from where we have also something like price quite often involved, is something that we see regularly. Yeah.
Thank you. I'll give it a couple seconds to see if another question comes in. While we're seeing if any other questions come in, and if not, we'll go ahead and end the session. Do you have any final thoughts?
Yeah, if you're interested, get in touch with us. Happy to evaluate with you the challenges that you have and see if such a data-driven approach could be useful. What we are doing also is look with you into the projects before you even getting started to work with us, to make sure the data is in alignment, and give you also some guidance on how to structure the data and how to get started with such an AI-driven approach. And another message that I want to convey here is, you might be, or you are likely to be already ready in order to use AI. Don't think you need to spend months or years to perfectly structure the data. Instead of getting all your data into a perfect format and then get in touch with us or use any other AI solution, just check what data you have already and see if you can start small. As I have shown, or as I have told you, 20-30 data points is a good starting point. Pick a project you're currently working on and see how this is working. Bring that to the end, get an early win, and then you learn what is a good way to structure the data. You learn what data, what inputs are relevant and important, and then you can build up the database from there. And maybe that data point that you collected 10 years ago might be not as relevant anymore. So this is something that we see quite often, that customers really try to get that perfectly organized data and then come back to us after 2 years then to only figure out, oh, we spend too much time in organizing the data. We still put it in a format that is not as convenient to use for AI training. So instead, let's get quickly to a solution and get started sooner than later.
Great, thank you. While you were doing that, and we did have another question come in. What would the limit be with the models you are using?
Depends on what's meant by limit. Maybe you could elaborate a little bit on that. I would say one limit, not sure if this is meant by that in the question, would be the amount of data points. As I said, 20 would be the minimum. Regarding the amount of inputs, we haven't reached the limits yet. There might be we have some limits defined by the number of ingredients, which is in the hundreds, but usually we can adjust that depending on how complex your problem is. We haven't reached any direct limits yet, but happy to see if we can reach it with your particular challenge that you have. And yeah, we are continuously improving the platform, are in close contact with our customers, seeing what challenges they have, and make continuous improvements. So yeah, I would say one limit is the minimum amount of data that we need, which is 20. But regarding the amount of inputs and the amount of objectives that you can define, we haven't really reached any limits. Limit of objectives, I see now. Well, I think by default it might be 128, but as I said, we never had a customer who reached such a limit. So, and even if this is like a threshold that we defined ourselves in order to make sure that that was not an accident, that too many objectives were set up. So not aware that we have an actual limit that might be a problem. The limit might be then that the platform will have trouble finding a perfect solution because those objectives are too competing to each other, right? It is still giving you suggestions that are within, that are realistic, right? And so when you are trying to optimize two things that are completely opposed to each other and too far away from each other, then it will give you something in between. And then if you add 10 more objectives that are also far off, then it will try to find a sweet spot, but it might not reach all the limits. So yeah, depends on exactly the use case. But if you have 20, 30 objectives, this is not a problem that we have.
All right, well, thank you. There doesn't appear to be any other questions in the chat box. So Matthias, thank you so very much for a great presentation. It was a very enlightening presentation. We very much appreciate it.